Hi everybody, it's Professor Mitchell. We're starting chapter 6 today on rational numbers and proportional reasoning. And we'll start by talking about the set of rational numbers. So at the end of this section, you'll be able to understand and explain different representations for rational numbers, equal fractions, equivalent fractions, and the simplest form of fractions, ordering of rational numbers, and the denseness or density property of rational numbers. So, of course, you know that a fraction looks like this, and the top number is called the numerator, the bottom number is called the denominator. Uses of rational numbers. One use is in a division problem or as the solution to a multiplication problem. For example, the solution to 2x equals 3 is the rational number 3/2. It's used to represent a portion or part of a whole, as in Joe received half of Mary's salary each month for alimony. That's kind of a depressing example, unless you're Joe. Another use is as a ratio. The ratio of Republicans to Democrats on a Senate committee is 3-5. And it's used in probability. When you toss a fair coin, the probability of getting heads is 1/2. Here are some rational number models. First, you see the area model. This is an area model of the fraction 1/3. Next is the number line model. Here is a number line representation of the fraction 2/3. And finally, you have the set model. Here's a set model representation of 3/5. To understand the meaning of any fraction a over b, where a and b are whole numbers and b is not 0, using the parts to whole model, we must consider each of the following. We must consider the whole in question, the number b of equal sized parts into which the whole has been divided, and the number a of parts of the whole that are selected. A proper fraction is a fraction a over b, where a is less than b, and a and b are both positive. Examples are 5/8 and -2/3. Now this seems to go against what I just said about a and b being positive. Notice they park the negative sign in front of the whole entire fraction. Okay, but that's the idea of a proper fraction. When you look at the fraction part, the numerator is less than the denominator. An improper fraction is a fraction where the numerator is greater than or equal to the denominator. For example, 8/5 and -3/2. So you know that improper fractions can also be written as mixed numbers. All right, here's an example of the number line model. They want to know what numbers are represented on the number line. Well, in order to answer this question, we're going to have to figure out how much each of these intervals is worth. I noticed that they only have marked off -2, 0, and 2. They did not mark off 1, for example. That would have been really helpful. So let's do this. We'll count starting from here. 1, 2, 3, 4, 5, 6, 7, 8. So the interval from 0 to 2 has been divided into 8 equal smaller intervals, which means each of those intervals represents 2/8, which is 1/4. So now counting from 0, going to the right first, I see 1, 2, 3. This is 3/4. This is 4/4 or 1, 5, 6, 7, and this is 7/4. Okay, and then going in the other direction, this is -1/4, 2, 3, -4/4 or -1, 5, 6. This is -6/4 or -3/2, and this is -7/4. So there you go. Equivalent or equal fractions. Equivalent fractions are numbers that represent the same point on a number line. And here is an example of all of these fractions represent the same number: 1/3, 2/6, and 4/12. And it's pretty convincing from that area model that those three fractions represent the same portion of that area. So 1/3, 2/6, and 4/12 are all equal. You can model fractions using fraction strips. So this brown bar at the top represents one unit or one whole. The pink represents 1/2. It's been divided into 2 equal parts. The green pieces represent 1/6, and the black pieces represent 1/12. They don't have a picture of 1/3 in this model actually, but I can at least see that 2/6 is equal to 4/12. 2 of these are equal to 4 of these. Fundamental law of fractions. If a over b is a fraction and n is a non-zero whole number, then a over b is equal to an over bn. In other words, you can multiply the top and the bottom of a fraction by the same number, and you get an equal fraction. So here they want me to find a value for x such that 12 over 42 is equal to x over 210. So the first thing I need to, I need to find this number n that they were talking about in on the previous slide. So 42 times what number equals 210? That's a division problem. 210 divided by 42, I believe that comes out to 5. Yes, so 42 times 5 is 210. And if I'm going to multiply the denominator by 5, I need to do the same thing to the numerator. 12 times 5 equals 60, which means x equals 60. Simplifying fractions. A rational number a over b is in simplest form or lowest terms if and only if the greatest common divisor, remember that, of a and b is equal to 1. That is, if a and b have no common factor greater than 1. So in this example, they want us to write each of the following fractions in simplest form if they're not already in simplest form. Starting with 28ab squared over 42a squared b squared. So what we're going to do is find a common factor on the top and the bottom that we can take out. And it turns out that that common factor is 14ab squared. The numerator is 2 times 14ab squared. The denominator is 3a times 14ab squared. So taking out that common factor, the simplest form of this fraction is 2 over 3a. And please feel free at any time to pause the video if you want to try one of these parts yourself. Okay, so in the next example, we're going to have to do a little bit of factoring, the kind we talked about. I think that was just in the last section. So, for example, remember that 3a plus 3b can be written as 3 times a plus b by undoing the distributive property. And the meaning of the square of a plus b is a plus b times itself. So a plus b times a plus b. And now I see my common factor is a plus b. So I take that out, and I'm left with a plus b over 3. Next, we have x squared plus x over x plus 1. The numerator has a common factor x, which I will take out. And that leaves me with x times x plus 1 over x plus 1. So we have our common factor is x plus 1. A lot of people will find it helpful to put a 1 next to this x plus 1. And then I can see that when I remove that x plus 1, I'm left with x over 1 which of course is the same thing as x. All right, continuing, we have 3 plus x squared over 3x squared. That definitely looks like it can be simplified, doesn't it? But it can't. 3 plus x squared doesn't have any factors other than 1. So in an algebra class, we would call this a prime polynomial. All right, only has 1 and itself as factors. And since neither one of those factors is 3 or x squared, that means there are no common factors on the top and the bottom of this. It's already in simplest form. However, if I were to park a 3 next to this x squared, like you have in letter E, then I can factor a 3 out of the numerator. That leaves me with 3 times 1 plus x squared over 3 times x squared. Remember, this is multiplication. And now I can take out the 3. And that leaves me with 1 plus x squared over x squared. Equality of fractions. So there are a few different ways that you could show that 12 over 42 and 10 over 35 are equal fractions. One way would be to simplify them both. Okay, 12 over 42 simplifies to 2/7, and so does 10 over 35. So that would be one way to do it. Another way would be to rewrite both fractions with the same least common denominator. Least common denominator, by the way, is the same thing as least common multiple. So use what you remember about least common multiple from the last chapter to find least common denominators. The least common multiple of 42 and 35 is 210. So remember earlier we multiplied the top and the bottom of this fraction by 5, and we got that it was equal to 60 over 210. If I multiply the top and the bottom of this fraction by 6, I get the same thing. I get 60 over 210. So that's another way to show that those fractions are equal. You can rewrite both fractions with a common denominator, not necessarily the least common denominator. And the laziest way to do that is to just multiply your two denominators together. So that will always be a common denominator. It won't usually be the least common denominator. So if I multiply the top and the bottom of this fraction by 35, I get 420 over 1,470. And if I multiply the top and the bottom of the other fraction by 42, I get the same thing. All right, and then a fourth way is to use this theorem. Two fractions, a over b and c over d, are equal if and only if a times d is equal to b times c. So sometimes we call this cross multiplication. When you multiply these two together and then multiply the other two together, if those two products are equal, then that means the original fractions are equal. So that would also work in this example. Ordering rational numbers. If a, b, and c are integers and b is greater than 0, then a over b is greater than c over b if and only if a is greater than c. All right, so that's pretty easy to illustrate using an area model or a number line model or really any of these models. Very easy to compare fractions when the denominators are the same. However, if the denominators are different, then you can use something similar to what we were just talking about. If a, b, c, and d are integers, and b and d are both greater than 0, then a over b is greater than c over d, if and only if those same cross products that we were just talking about, AD is greater than BC. So for example, if you were comparing the fractions 4/5 and 11/12, I can see from this area model that 11/12 is greater than 4/5. If I wanted to verify that, I could write, whoops, forgot to turn my pen on. Sorry about that. Let's see, where'd it go? I wanted to verify that, write 11/12 and then 4/5. And then if I look at those cross products, 11 times 5 is 55, and 12 times 4 is 48. So since 55 is greater than 48, that means 11/12 is greater than 4/5. Given any two, this is called the denseness or density property of rational numbers. And you don't have anything like this with whole numbers or integers. So this is a really fascinating property of rational numbers. Given any two rational numbers, a over b and c over b, there is another rational number between these two numbers. All right, so I don't care how close together these fractions are, you can always find another fraction between them. So right now they're just talking about fractions that have the same denominator. In a little bit we'll talk about how to do it when the denominators are different. Okay, so for example, let's find two fractions between 7/18 and 1/2. So one way to do it is to write those fractions with a common denominator. The least common denominator would be 18. So if you multiply the top and the bottom of 1/2 by 9, you get 9 over 18. So now we have 7 over 18 and 9 over 18. Now they asked for two fractions. It's easy to see one. 7/18 and 9/18. Clearly 8/18 is between those two. So we'll simplify that to 4/9. So we have one fraction that's between those two. And now we can repeat that process. Well, actually, if we make the denominators bigger than 18, then it'll be easy to see more than just the one fraction. So if we find two fractions, I think that's supposed to say between 7/18 and 1/2. But with greater denominators. So for example, if we made the denominators 36 by multiplying the top and the bottom of this by 2 and the top and the bottom of this by 18, we find that those two fractions are equal to 1436 and 1836. So I can actually see three fractions that are between those two. 1536, 1636, and 1736 are all between 7/18 and 1/2. All right, now there's another kind of neat way to find a fraction between any two fractions, and that is to use this theorem. Let a over b and c over d be any rational numbers with positive denominators, and suppose a over b is less than c over d. Then it turns out that if you add the numerators and add the denominators, which is how I'm always reminding my students is not how we add fractions, right? That is not how we add fractions. But what it does give you, it gives you a fraction that's between those two fractions. And I wanted to give you a scenario that would help you kind of understand why that works. So suppose you're taking a class where you take an exam and you score 84 out of 100 points, which is 84%. And then a couple weeks later, you take a quiz and you score 18 out of 20 points, which is 90%. Now, if this class is using a points system, then between those two assignments, you've earned 84 plus 18, which is 102 points out of a possible 120. And doesn't it make sense that if you got an 84% on the exam and a 90% on the quiz, that would put your overall average somewhere between 84 and 90%? And it just so happens that 102 out of 120 is exactly 85%. I wouldn't expect it to end up right in the middle because the exam counts a lot more than the quiz. But it does make sense that by adding the numerators and adding the denominators, I would get a fraction that's between these two fractions. So that's another way to find a fraction between two fractions. So if we go back, all right, a very easy way, you just take 7/18 and 1/2. 7 plus 1 is 8. 18 plus 2 is 20. So that's telling me that 8/20, which simplifies to 2/5, is a fraction between 7/18 and 1/2. And that's going to do it for this first section of chapter 6. We will see you next time.